now that you had an introduction on what torque is considered to be, we are going to do an example. So we have a wheel here. We know that wheels have the potential to turn. So you can see that there's 3 forces that are acting on it, and we're going to pay attention to not only the magnitude of those forces, but specifically where they are applied, because that is kind of the big idea with torque. Is it's not all about the force, it's where that force is applied to potentially get something to spin, or if it's already actively spinning, that's what it comes from. So first we are going to find the net torque on the wheel in this figure out about the axle 0 or capital O, which is in the middle of the picture. And there's 2 radiuses. One is in kind of an inside wheel with radius A, the other one's the bigger on the outside, and that one's radius B of 25 centimeters. So the forces are labeled there. So if I want to find net torque, then remember, torque is, to get one individual torque, you need the force, the radius, and then that sine of theta, the angle between them. So if we look at the picture here, I'm just going to talk specifically about force 1. So it's going straight to the right, and then our wheel at that moment, if we look at the turning portion, it's applied right at that kind of tangent line to the outside of the wheel. So the radius is going to be perpendicular to the force. And we know if you have FR sine theta, if that theta is 90 degrees, if it's already perpendicular, then this term just turns out being 1. Okay? So if we look at the other forces here, the 30-degree angle that's given is kind of just extra information, because if you really look at it, if you're pulling that side on the wheel, it's still perpendicular to the axis A. It just happens to be, if you had a horizontal line here, then that force is 30 degrees below it. But it has nothing to do with the fact that it's force 3 is already perpendicular to the axle A. So what we really need here is to add up all of our individual F times R's, since our thetas are all 90 degrees. Everything's already perpendicular. So we'd kind of have like F1 R1 plus or minus F2 R2, and that would keep going, add up all your little individual torques. So next we need to, just like we did with Newton's laws of motion when we were adding up forces and trying to find a net force, we need to take direction into account. So I need to make sure I think about which way that these forces could potentially cause rotation. If, for example, if I pull on force 1 this way, that would cause the wheel to spin in that direction. Okay, but if I pull on force 3, it's going to cause the opposite direction rotation. Okay, so now we can add up our individual torques on the wheel. So the force 1, I'm going to choose things that could cause this direction of rotation just clockwise to be positive, and I'm going to cause things that will work against that, going in the other direction, and then choose that to be my negative direction. Okay. So F1 and F2 are going to kind of work together in this way. So that's your positive direction. F3 will be working against it. So we would have F1 times its radius, which is B. I'm going to write it out in variable form. F2 also times B. And then since F3 is going in the opposite direction, it wants to pull in the counterclockwise direction, we have F3 times A. All right. And we can plug in some numbers to that because we have our numbers in the picture and we know how far we are away from the axle. So if I just start substituting those in, F1 is 10 newtons, so I'd have 10. Since the radiuses are in centimeters, be careful here. You want to make sure you're in your SI units. So B would be 0.25. We put that in meters. Plus F2 is 9. And then F3 is 12. And its radius is a little bit smaller at 10 centimeters. Okay. And if you add and subtract these together, we find that the net torque on the wheel is about 3.55. And then if we think about the unit that goes with this, a force is in newtons, a radius is in meters, so you basically have Newton meters, newtons times meters for the unit. And that is our solution for part A. Okay, so now that we have our net torque on the wheel, that's finishing off part A in the problem, we can move on to part B, where we are trying to find the magnitude and direction of force that is needed to be applied to that smaller radius A to keep the wheel from spinning. Because the fact that we got a net torque here tells us that those force 1 and 2 are enough to get the wheel in motion in that clockwise direction, and force 3 is not quite enough to resist it to get it to stop. So we need another force added into the wheel if we want to keep it from spinning. So the goal for part B, again this was part A, so the goal for part B is to get no spinning. So we want a net torque of 0. We want everything to balance out. Okay. So I know that we already have a torque of 3.55 Newton meters. Okay. So if I want all of those to balance out to be 0, I know I've already got this positive 3.55. So I know I need to resist that in another direction. So I'm going to subtract another torque. Okay. So we'll call it torque 4. All right. So we would need some force 4, and then it says that we're going to apply it to radius A, and that was just some given information in the problem. So if we applied another force to that smaller sort of orange colored axle, we're going to be needing to multiply that by A. So you've got your force times your radius. Okay. So then this tells you that this has to balance out that positive torque. So we'd have F4A being equal to 3.55. And then you know that A is just that 10 centimeter radius, so 0.1 meters. So if you divide 3.55 by 0.1, you get that F4 has to be, that extra force has to be about 35.5 newtons. Okay, so that's the magnitude of it. And then we need to talk about the direction that needs to be applied. So overall, the wheel, since we got a positive torque in part A, so we know that the wheel is spinning in this clockwise direction. So I need this force to work against that and cause rotation in the negative direction. So if basically this force needs to be something like F3 in the picture, where it actually pulls in that kind of overall leftward direction. If we were on top of the wheel, if we were on the side of it, it would need to be pulling down. If we were on the bottom, it would need to be pulling to the right. So it's kind of, the goal of this in terms of direction is to cause counterclockwise torque. So that's your specific direction for that. And there we have an example where we're adding up a bunch of different force times perpendicular radiuses to get a net torque, and then we can solve it for when we want the wheel to stop as well. On to the next video.